Thank you very much for the introduction. So my name is Hsin-Ni Ho, and today I will introduce my research, and the topic is beyond physical stimuli, understanding and designing human touch experience. Actually, I write perception, but I prefer experience. So I want to move to the next slide. Okay. Yeah, so just a quick self-introduction. So as some of you might know, my expertise is haptics. Haptics is basically regarding the perception and engineering of touch. So basically, I research about the sensory information processing of touch, and want to apply it to the design of human interface that can be applied in, for example, remote communication, virtual reality, various type of ICT technology. So I'm from Taiwan. So my background is mechanical engineering. And so I got my master in Taiwan. After I graduated, I went to MIT for the PhD. Which is still major in mechanical engineering. And at that time, I kind of realized that I'm more interested in human than in machine. So after I got my PhD, actually my PhD is about haptics, human interface. So I already started to study about the human-centered design, how to present information to human. But in order to learn more about how human process information, I decided to do my postdoctoral research in NTT. That's the reason I came to Japan. So I joined NTT Communication Science Laboratory, and there I learned and conduct the research about sensory information processing. And I have been there for 14 years. After that, I came to Kyushu University and the Faculty of Design. So quickly summarize my expertise is that mechanical engineering, human sensory information processing, and media design. So I want to first start my talk about why touch matters. I mean, because I think touch is still quite minor when I introduce about my own expertise. Lots of people will be quite surprised. And first, I just want to emphasize that touch is quite important in our life, although probably for most of the time, lots of people doesn't really think too much about it because the sensation is kind of in the background. But in our daily life, we use touch to understand our environment and to recognize the object. For example, if you want to find your key in your bag, probably you don't need to put your head into the bag, right? You could just your head and then you kind of search and you can find your key using your touch. And touch is also important to feel the 質感, the material perception, whether, for example, 質感 of the clothes or whether this surface is smooth or rough. It is something, the information that basically if you want the most reliable information, you have to use your touch. And the other aspect of touch is to communicate. It's more effective to communicate emotions. For example, we call it social touch, like a hug between family and friends, holding hands. This kind of touch conveys emotion, and it also provides a sense of security. So that's why lots of kids like their security blanket or like to hold this kind of soft toy when falling asleep. So touch has played different roles in our daily life. And I just want you to take some time, 1 minute to think about actually what will happen if we lose touch sensation. What will happen in our daily life? Basically, we use our hand, for example, to use keyboards, when using our computers and we're working and holding pens. So actually for any object interaction, for interpersonal interaction, if we lose a sense of touch, basically we have no feeling. And if we have no feeling, basically we have no control. It's really difficult to control our own behavior. So actually it will be pretty problematic. You could kind of imagine in the degrees that you are wearing a really thick glove during the daily life, and you lose a lot of information from the skin. And as I said, touch is quite important, and there are kind of several complementary societal challenges have been faced. For example, in the case of without touch, first, we all know touch is important to maintain kinship, like the physical interaction, for example, between caregiver and kids, or between this kind of interpersonal like communication. But right now, we use remote communication a lot, right? For example, now I'm giving talk online. And this kind of online communication, or even in virtual reality, basically touch is still almost of time not available. And it causes a problem, for example, lack the sense of being together, and the engagement is quite low, especially, for example, like online class, this kind of things. And a while ago, we have the problem over COVID. And at that time, we have social distancing. Of course, people shouldn't have physical interaction. We should keep the social distance. And during that time, it was widely discussed as far as I know, in Europe or in US about skin hunger. Yeah, because Chi Sensei is from UK. So yeah, so skin hunger is actually physical interaction is quite important for we human. Without touch, and we will have the problem of skin hunger, and it will cause the issues for our immune system, cause stress, depression, and sleepless. So actually it causes a lot of mental and physical problems. And because now our society is changing, and that we are getting, that more and more we are aging, and then less kids, and so there are lots of problems about loneliness, which is also related to like the skin hunger, because they lack physical interaction with others. So that's why I kind of feel it's really important to develop a technology, kind of enhance this kind of, whether there's a possible way to provide a way to enable the physical interaction, and also to enhance the sense of presence, the sense of being together in different scenarios. For example, like VR, remote communication, those mediated communication. And the other thing is actually haptics there is a growth, and also the real application of haptic technologies. For example, like recently the head-mount displays or the Apple Vision Pro, the controller are embedded with the vibrational motor. So you can feel some vibration when you, for example, playing games. So there are also lots of light switch and Sony DualSense. Also, actually, Sony has a haptics group. They really put a lot of effort in providing the haptics experience. So, and also in XR and Metaverse, there are different types of gloves that provide the vibration, so kind of to enable you to feel that you can touch the virtual objects when you are in VR. On the other hand, in other industrial like automobile, actually in automobile, there is also lots of haptic feedback is provided, because one example is, for example, like touch screen. When using touch screen, you really have to look at it. Otherwise, it doesn't like the mechanical like buttons or knobs. You could just adjust your air conditioner without looking at it. For touch screen, that kind of feedback is lacking. So there is a trend that they try to put the haptic feedback back for the haptic touch screen. So it's easier to operate during driving. And of course, in medical applications, there are also like the surgical simulation. Actually, it's providing force feedback for the doctor to practice before the surgery. So they are able to do remote surgery. So there are lots of applications. So basically, what my lab want to do is, in my lab, we first want to survey how human process touch information. And then So our development is very human-centered. We first want to understand human, and then we want to develop technology based on this kind of human, the perceptual property of human. And then two major directions currently I have. First is to share the Shizukan material property. The other is to assist the effective communication to convey the emotion. And hopefully in the future, we could expand the capacity of current ICT communication and to enhance the quality of life. So it is basically why I want to research touch and why it is important. Okay, so there will be 4 parts. And the second part, I want to introduce my research. So I mentioned my 2 main directions is about Shizukan sharing and effective communication. Today I will kind of more focus on Shizukan sharing and the basic sensory information processing part. And this is actually my first work when I was a PhD student in MIT. At that time, we focused on temperature information. So when talking about touch, basically the perceptual dimension of touch can be divided into 5 major dimensions. So as shown here, of course, temperature, warm or cold, is very important. When you touch something, you definitely can feel that. So, and also in order to convey the realistic texture and emotion, I think thermal information is very important. For example, when we touch different materials, the metal feels cold, the wood feels warm, the fabric feels warm. Even they are at the same physical temperature, they are all at room temperature of 25 degrees C. But we feel very different. It is because physically the heat transfer is different. And so of course, what kind of material temperature give the major information. So that's why I decided to focus on this for my PhD work. So basically, at that time, we are kind of think. So in virtual reality, we have the virtual object or remote object. We want to interact with it. Of course, we want to provide the feeling that the user just feel like they actually touching the object. So we want to replicate the thermal characteristics of the object. And we want to provide a thermal sensation associated with touch. So what we did is we did the modeling of what happens physically between the hand and the object, the focus on heat transfer, the thermal interaction between the hand and the object. And basically, our skin temperature most of the time is higher than the object temperature. So our heat flows to the object. That's why, and then our skin temperature decreased. So that's why we feel cold when we touch different things. So we want to model this skin temperature change, and we want to represent this skin temperature change with a thermal display. Okay, so for example, we could have a model and then calculate skin temperature change when touching metal or touching wood or touch stone, whatever. And then we could represent this information with thermal display. And hopefully the users will feel that they actually touch metal or wood when they interact with the object. So basically what I did is thermal modeling. It's very classical mechanical engineering approach. And basically, so I model the initial temperature of the hand and the object, and also the object's material properties. Also, I consider the contact force, and for the human side and for the object side, consider surface roughness and its geometry. So I have a model which involves mathematics, quite complicated. In the end, I kind of could have simulated this kind of curves, which tell me that when touching, for example, copper or when touching the foam, stereo foam, how the skin temperature will change. I even can model, for example, for aluminum, for metal, when you, for example, that is what we use in the kitchen, right? Aluminum foil. When you touch that, it doesn't feel cold at all because it is very thin and it is warm up by our hand instantly. But if you touch a metal block, you will feel very cold. Even though they are the same material, but because of the geometry, the difference in thickness, your feeling will be different. It is also because the physical interaction, how the skin temperature change. It actually is different. Actually, the response based on the thickness, so that's why we will feel different. So the model is able to predict this as well. So this is my first series of works. And based on that, we have a thermal display, and then we did human testing, and then demonstrate that young people can actually recognize the object based on the simulated material. So the next part actually goes to when I came to Japan. I mentioned that I'm more interested on the human side, especially how human processes sensory information. For example, previously I more focused on the physical side, so I could have a physical modeling, calculate what happened in the skin. But from the skin, how the information is transmitted to the brain and how the perception is established. At that time, I'm still not so familiar with that, so I decided to research in this direction. So basically, if I kind of try to summarize what I have been doing so far, I would summarize this that the cutaneous perception, the skin perception, the active construction of cutaneous perception. What does active construction mean? It means that actually the perceptual experience actually emerge from the integration and interpretation of sensory signals. Okay, that might be a little bit vague, so let me go into more detail. So this is a slide I often use in my virtual reality class. So in virtual reality, we want to create virtual reality. We need to think what is reality. So I think probably that's a definition shared by quite a lot of researchers in VR. So reality is a sensory experience created by the brain based on the information from the five senses. So brain actually play a very important role. So basically we have physical input, and then we could kind of treat it as sensory information. And then our brain, constructed by a brain, means that we have so many information from our eyes, our skin, our ear, and then our brain will try to integrate all this information to make sense what is happening right now, what is the status of the physical world. So our brain will do interpretation and integration of all the informations. And then we will have a sensory experience. So for touch, this is the case. We have physical inputs, and in our skin, we have different sensory receptors, more than 6 actually. And then different physical stimuli will activate different receptors. And then the information will transfer to the brain. And then we will have different skin sensations, like the basic ones. And then those about the materials, for example, whether it's wet or dry, and even higher level, whether it feels pleasant or not. I kind of think I probably will speak more than 20 minutes. Would that be okay? 大丈夫そうですか? Okay, yeah. And so basically, I'm going to give you some examples based on my research. I want to tell you actually the touch or the skin sensation is an active construction of tactile experience. So I'll give you some example of the cases that the sensory input is not consistent with the perceptual output. So why it happens is because our brain is doing something in between, because how our brain processes information. And so first I want to talk about temporal integration between temperature and thermal and tactile inputs. So basically, thermal and tactile sensory systems are independent, and they are very different in temporal processing speed. So when we touch something on the skin, the information has to transfer to our brain. So you could kind of consider it as a 1 meter distance. And the fibers to convey touch is very fast. but the fiber to convey temperature is very, very slow. So if you touch a surface like this, when the thermal and tactile are input to our skin at the same time, actually the time it reach our brain will be very different because their speed is very different. But we didn't feel that. We always feel the temperature happen at the same time when we touch, right? For most of the time. So this means that our brain is doing something to compensate this type of sensory processing speed difference. So we did an experiment. We present thermal and tactile stimuli at different interval, time interval. Sometimes thermal first, sometimes tactile first, sometimes they are at the same time. And then we found a really interesting result. So the horizontal axis of the result plot on the right-hand side is the SOA, is the time interval between the thermal and tactile. And the right-hand side is tactile first, left-hand side is thermal first. And the big zero means the physical simultaneous, means that they are present physically at the same time. And we look at the peak. The peak means that this is the timing where people think. Most of the time, people think thermal and tactile happen at the same time. And you could see it is not consistent with the physical zero. It is shifted to a left. Basically, when thermal stimuli comes first, people tend to think they are more simultaneous. And this is because thermal is slower. So if thermal comes first, for most of the time, it is easier for the brain to process. This is some general mechanism. Also for visual, auditory, visual, tactile. Basically, the slower sensory modality has to come first. At that time, you will feel more simultaneous. So this kind of demonstrate that even sometimes stimuli are not present at the same time. People who feel they happen at the same time. So there is a window. The pink shape is the window. Within that window, people will feel that the stimuli happen at the same time. So the other thing is about wetness perception or liquid perception. It is something I am very interested in recently because I mentioned on our skin we have many receptors for touch, for temperature, for pain, but we don't have receptor for wetness. We don't have a sensory receptor for wetness, but we can feel it is wet, right? How do we do that? And basically how we did is that the wetness, the perception of wetness is integration between the thermal and tactile input. And it is multimodal integrated in our brain for most of the time. If it is cold, and if you feel the pressure, and then for most of the time people will think it is wet, or people, the head is in the liquid. So that is why sometimes if in the winter, if you have your laundry outside, sentaku soko nyoku toki ni, if you try to take your laundry, for me at least, I was sometimes confused whether it is still cold or it is still wet. This is because we don't have the receptor, so actually we are not sure. So this kind of demonstrates this process. So based on that, we could do something very interesting, is that we could manipulate the sensation of wetness or the liquid perception. So basically, liquid perception of wetness can be enhanced or suppressed or modulate by changing the sensory cues. So in this particular study, we had subjects' head in real liquid. So they put their head in the liquid. But in that liquid, we used to discuss liquid so that we could kind of suppress the tactile input on the hand. And we use LED light to provide the warm stimulation. This kills the cold sensation from the water. So we try to kill the cold sensation from water, and we try to kill the tactile input required for liquid or wetness perception. And this is our result plot on the right-hand side. Basically, when the LED light is off, the black bars, and people will feel liquid. We ask them to rate the liquid perception. People feel the liquid. But when the LED light is on, when the thermal stimulation is provided on the skin. So this thermal stimulation is selectively provided to the skin. It doesn't heat up the water because of its wavelength property. When it is on, you could see that the liquid perception dropped to about 50%, which means that people start to feel confused. This is something you really have to try yourself. I guess it is very difficult to imagine. You really, if there's a chance, yeah, I could have a demo. You really need to try, but it is something quite amazing. The other is the apparent motion. So here is the visual apparent motion. So basically, there are two dots that is flickering. Most of people would feel that it looks like one dot is moving from left to right. So this is actually a classical illusion in vision and called apparent motion. So we also try whether it happens to temperature. So basically the setup is so the visual is two dots. And in thermal, we have two stimulator Peltier on the forearm tube. And then we activate, so one stimulator is activated first, and then after, for example, 4 seconds, the second stimulator activates. So basically, it's trying to have something similar to the visual apparent motion. And actually, we found that apparent motion, this kind of illusion also occurs for the thermal, in the thermal case. So the right-hand side is, we ask the subject to draw how they feel. And then the different hands means different SOA, the onset timing difference between the first stimuli and the second stimuli. So we found actually the second one, the 6 seconds, for the first and second, the SOA is 6 seconds. Actually, it's most optimal. People really feel a smooth motion just from the 2-point stimulation. So after these 3 examples, what I want to say is that the physical stimulus, the perceptual experience sometimes does not directly reflect the physical stimulation. This is something super important. And actually, our perceptual experience was based on the sensory inputs, the information from different modalities. And our brain actually is working very hard, trying to integrate information or try to compensate what are missing and try to do prediction. And in the end, we are able to have experience that, that is meaningful across different modalities. So this comes to the last part is about the designing touch experience. Because of this kind of property, actually we are able to design experience because we don't need to reproducing the physical stimuli directly. For example, in VR, if I want people to feel wet, I don't need to have a bucket of water. That would be problematic. We don't like water get near to our equipment. So we can, through this kind of manipulation, leverage the principle of perceptual construction to create a new experience. So the last part, I will introduce 2 of my VR-related study. First is we try to create wetness illusion in VR. This time, actually, we combine heat with wind pressure. So as I said, wetness required temperature and tactile input. Previous research all deal with cold, and this time we try the wall stimulation. And we found it works. And in VR, we kind of want to see how visual information influence the experience. So in VR, we have 2 different scenarios. One is campfire, which is now wet. The campfire is dry. And the other is kettle and steam. And if you look at steam is wet. So basically, we have one incongruent and the other congruent condition. And we want to see how visual information influence the wetness perception. So right-hand side is the data, the upper one is campfire, the lower one is steam. Basically, we found that And the strongest when this perception is produced by high thermal stimulation and high pressure combined with the congruent visual experience. Under this case, like this box, people could feel the probability is almost close to 100%. People feel wet. Even there's no physical wetness, they just in VR, they look at the cattle skin and they feel the heat and wind pressure we provide. Yeah, so basically the key findings I want to say is importantly, a tactile or cutaneous skin perception is not the direct reflection of physical stimuli. Basically, this is true for other modality as well, for example, like vision or the brain actively constructs perceptual experience through the integration and interpretation of sensory signals. So understanding this mechanism can enable the creation of the sensation that do not physically exist. And that is very interesting. Yeah, and I think this opens new possibility for designing richer and more meaningful and more human-centered digital interactions. So thank you very much.